Marzyeh Ghassemi is associate professor at MIT with joint appointment in ECS and IMES. She also holds research affiliation at Leeds, CCEL, and IDSS. Her research sits in the intersection of machine learning and healthcare, focusing on reliable and ethically grounded AI system. Her scholarship spans leading venues from NeurIPS, KDD, Triple AI, Nature Medicine, JAMIA, and highlighted by MIT News, Boston Globe, Forbes, and Huffington Post. So today she will talk about the pulse of ethical machine learning in health. So with that, I will give this to our speaker. Thank you.
Thank you. I'm just going to make sure that I can share my screen. All right. So I'll share screen.
Okay.
And then you'll have to tell me if the presentation mode works well.
I can see the screen.
All right. And do you see one slide?
Yes, all good.
Okay, great. So hi, everyone. I'm Marzyeh Ghassemi, and I am going to talk to you today a little bit about the work that my lab does. I'm going to focus quite a few of the examples are focused in health because that's the area that I primarily work in. But I will also say as a machine learning researcher these days, AI and ML is being used in almost everything. And so we also have other examples. I have other examples that sort of span other human-facing settings. My lab focuses foremost on constructing robust methods for fair results. And so that's, whether we're talking about predicting a diagnosis accurately in a healthcare setting or trying to debias a model for a hiring setting. I think we try to understand there's a lot of shared components of robust prediction that aren't unique to healthcare, but are maybe best exemplified in healthcare. We try to understand those. Once you have a robust model, it may or may not work well in a healthcare setting, either because, you don't have the right data, you don't have the right algorithm, or just because, the humans in that setting don't need it, don't want it, or don't know how to use it. And so we also try to understand how machine learning deployments will make humans better or not in healthcare settings. I always start with this example, but I'll breeze through it because this is an audience that I think is extremely familiar with it. Which is we are often given a very specific case example, right? Something like, can you make a triage model for somebody in a hospital setting? And in this case, what you would do is see a bunch of chest x-rays, and then you would want to predict the ones that have no finding because the patient is healthy so they can go home. And we as researchers know how to do that. We follow this pipeline, we deliver. And in this case, if we already know what we want to do, and you could pick any use case here, right? But for us doing model-based chest x-ray diagnosis, there are large publicly available data sets available for chest x-ray diagnosis specifically, but for any other constituent problem, you might have a private data set, you might be working on data within your institution. As long as you have a large sample size, you can take this 700,000 images, you can train some sort of model, whether it's a convolutional neural network, which we use in this case because it's on an image. You could also be using a large language model, a vision language model, a recurrent neural network. And then you predict something, right? If we're doing predictive modeling, we have a specific label. If we're doing generative modeling, the thing you want to predict is other versions of the data itself, right? You're just generating new versions of the data. And in this case, right, we found that this model had state-of-the-art performance on this task, which is great. The thing that my lab tries to think a lot about is not just can you get to a specific, yes, we can predict that, or yes, we can generate that, because the answer is always yes. our models are good enough that if you have data, we can probably get there. I think the question is, should we? And that's a question that I think all of us are both A, grappling with, and B, should be grappling with. This was a nice review that came out this year, showing that, medical large language models do quite well on discriminative tasks, even when compared to human experts in many of the cases. And in generative tasks, obviously, they don't have a human baseline, but they're getting better based on some automated metrics, right? If we just pick one of these tasks, right? So the most popular one is Med Q&A, and maybe you've seen this. This is like an open data set of medical question answering. It's something that a lot of people benchmark to, including private companies and researchers and PhD students. The dotted lines, the dashed lines, are closed source models. The filled lines are open source models. And then the colors indicate whether the model was prompted, pre-trained, or fine-tuned with data for a specific task. And you can see that in many cases, we have models that are getting close to this human expert level, or in some cases, maybe surpassing it, depending on how you do the measurement and the evaluation, and that's its own can of worms. And so, each of us has papers, or will have papers, many papers in the future also, where we pick a task and we beat a benchmark and we show that we do really well on it. And they'll be added to this graph. The question is, should we be taking those models, getting them certified, and then allowing them to give advice to doctors, or maybe even directly give advice to patients? And we're not so far from that, right? Like, we already have FDA regulated devices, right? For both AI/ML enabled devices, you can be authorized by the FDA across a range of subspecialties. And, as a sidebar, if you're doing something in an administrative setting, right? Like, this applies to, these diagnostic devices. But if, for example, you're doing something in an administrative setting, so you're completing a note, you're filling out a patient billing record, you're drafting messages between patients and providers. So far, the FDA has been pretty clear that that's not their domain, right? That does not need to be validated or certified by them. Several European entities have actually come in and said it does need to be validated by their equivalent entity. But we, in the United States have, I think, pretty clearly so far said this is not the domain of the FDA or another regulatory body if it's this clinically adjacent administrative thing. But even if we're being regulated, right? Like, even if we're squarely in this FDA regulated space, the way that we ask for information to be regulated is often very limited. So we often perform, aggregate measures, and aggregate measures often hide subgroup underperformance. And so we had a paper so long ago now, in 2021, where we really tried to highlight how easy it is to do very sensible, normal modeling procedures and get a really bad result, where you get an average that's good, as I described, but 700,000 images, a convolutional dense net, like, that's, trained, highly performant, AUCs of 0.859, better than anything published at that point to date for this task. But we're reporting an average, which again is pretty common. We don't often do subgroup checks. When we do subgroup checks, they're often done at very sort of high levels, and we don't often look at intersections. And so when we did that for this paper, we found that the false positive rate, which is like an underdiagnosis rate, it's how often you're wrong on people who are actually sick and you say they're healthy, it's much higher in subgroups that you might imagine it would be higher in: female patients, young patients, Black patients, and patients on public Medicaid insurance. And this is bad, right? This is undesirable. But I think what's maybe scary or worse about it is that this is just one task. It's one application, right? And we're demonstrating that this can happen in this one application. One of the reviewers for this paper actually said, this is like a silly scare tactic. This is one thing. This wouldn't happen in other cases. Like you probably tried this in a bunch of other cases. This is the only one it did. You had these gaps in. But that's not true, right? Like this is a result that's been replicated in several papers and several studies. It's just not something that we're focused on as a community right now. And so one of the things I try to advocate really hard for is this idea that, of course, we can develop anything, but we want to think really carefully about why we're developing it and how it might be used. Because as developers, we shouldn't just wash our hands of the use cases. I want to walk through I think I have 3 examples of recent work that I think is interesting and pertinent to this point. So the first is, I think everybody on this call knows what a shortcut is. But machine learning models rely on statistical biases called shortcuts. That was invented by the vision community, but I think it's pretty pervasive now to make predictions. And it's, where you see a model that looks at a cow and it sees a cow on grass, and so it knows it's a cow. And it sees a mole and the mole is benign, it knows it's benign. But then as soon as you put a cow on an ocean, it's an orca. As soon as you take exactly the same mole and add any markings around it, it thinks that it's now malignant, not benign. And this is because of sort of reasonable statistical assumptions that models make, namely that large white and black things in oceans are orcas often, right? We don't see a lot of cows frolicking on the beach. And when you make marks around moles, statistically speaking, they tend to be malignant, right? And so in some ways you can't fault the model for thinking this. And these are kind of fun, like, well, at least the orca one is kind of a funny use case because you can see it. You can see why the model might have like seen a feature in the picture and then made a judgment that way. It's a lot less funny when there are features in text and in medical images that humans cannot extract, but machine learning models can. And then those are used. So, I can tell that the cow is on ocean. And so when it classifies the cow as an orca, I'm like, oh, I see. I cannot look at this medical note, and we tested doctors, they can't either, and tell whether this person noted in the record is black or white or male or female. But machine learning models can, and they can do so with extremely high performance using statistical differences in how clinical staff talk about different patients. Okay, so we can't tell, human doctors cannot tell, but for machine learning models, extremely high performance. And it's even worse for medical images. In medical images, there's just statistical information in the high frequency spectrum of these images that might give an indication that somebody is more melaninated. And our eyes don't do fast Fourier transforms. And so radiologists cannot look at this image and, for example, tell whether somebody might self-report black or white race. But machine learning models can. So think about the last thing I said, right? Like if you have a shortcut, you could sort of make a bad decision based on that shortcut and combine that with this, which is there are some shortcuts that only machine learning models can see. So we wanted to test if you train machine learning models in medical imaging tasks to predict important clinical outcomes, will they learn these shortcuts by default? And will they use those shortcuts to do more poorly in subgroups? And so we took 3 different domains, radiology, ophthalmology, and dermatology. In each case, we trained a machine learning model to convergence until it could predict the clinical task for each of these data types. And then once it was well trained, we chopped off the head of the model and forced it to predict demographic information about the patients, which it did not have access to. So for example, we would take the ophthalmological model, train it to predict retinopathy, and then we would chop the head off and say, now tell me what this person's age is. And it wasn't trained to do that, and it wasn't provided with that information. So if it learned it sort of secretly, right? What we found is that across all of these tasks, state-of-the-art convolutional neural networks, trained with vanilla optimization, which is called empirical risk minimization. That just means do best on average. When you train them to predict disease, they encode demographic attributes such as sex, age, race, and intersection of sex and race. And the more that they encode those properties that they were not trained to encode, the more that they have a predictive performance disparity along those attributes. Put a different way, the more that I know who is male and female when I'm predicting retinopathy and ophthalmological images, the worse I will do on predicting retinopathy in female patients. Those two things are correlated. That's what the line is showing. Okay. So this is not good, right? So we proved the thing that we didn't want to be true, but is true, right? Information that humans do not have access to when they look at these medical images in most cases is easily extractable by machine learning models when they're training to do a clinical task. And then they do use those shortcuts to make incorrect inferences about subgroups. Can we fix this? Well, there's lots of modern optimization methods that are actually pretty good at forcing the model not to do best on average, which is what empirical risk minimization does, but to balance performance in different subgroups that either you explicitly identify or that the model finds during training. So for example, if you look at this graph, this is a Pareto plot that all economists love. And so we were forced to put one on the paper by a reviewer. On the x-axis, we have the overall performance. Right is higher, right? So you want models that land, and every dot is a model. And so we want models that will land on the right-hand side of that graph for highest overall AUC, which is the thing you usually perform or report. And then on the y-axis, we want things that are very fair. So we want the gap to be very low between any two groups. And you can see in this plot, we're predicting cardiomegaly in chest x-rays. And the thing that we're looking at, the two groups that we're looking at for difference in performance are old patients and young patients, because age is in the parentheses. But you can see that we have the same graph here for all of the different tasks that we're looking at, and for many of the attributes in parentheses that we were trying to do evaluation with respect to. And the story is the same in most cases, which is empirical risk minimization often does very well on average. It's often on the right-hand side of the plot, but it has a big fairness gap. It's often sort of towards the top. However, you can choose subgroup robust, group adversarial robust, or generally robust model optimization techniques, and those will stay at about the same horizontal level, about the same overall performance, but it shoves the fairness gap almost all the way down. And so these are fairness gaps that we would be fine with because they're within error tolerance of model training between two subgroups, right? Less than 5%, in some cases, almost down to 0%. That's great. But this graph, all of these graphs are what happens when you take data from one site and then train a model, and then you test it on unseen data from the same site. So you would train on data from Massachusetts and test on unseen patients from Massachusetts. What happens when you train on data from Massachusetts, get the best model, right? You have these Pareto optimal models on the front, and then you throw these models over to colleagues in California at Stanford and say, evaluate on your data. It turns out that locally optimal model fairness does not transfer under distribution shift, even very mild distribution shift, right? Massachusetts hospitals are not that different from California hospitals, especially with respect to diagnosis of chest x-rays, right? But here you can see that some models, so first, all models get worse, which is normal. It's normal for models to do worse on unseen, out of distribution data than data from the same source. However, what's sort of concerning here is that even though everything gets worse on average, everything shifts over to the left, the fairness gap increases dramatically. And some models that were optimal are no longer optimal. And so if you would have picked this model as your operating point or this model as your operating point, and then deployed that model to Stanford, you would have been behind the optimal point. It would have been better off if you would have chosen another less fair model from Massachusetts that would have done better, been more performant, been more fair in California. And so the first thing that I think our group has sort of learned to date, many times over, but this is a great example of it, is that human data is really tricky, and we really need to start testing models on the data, from populations they're going to be used on, but that's not the norm right now, and it should be. The second thing we think a lot about is not just like data and shortcuts and, how things are distributed, but also directly about algorithms and how algorithms can be improved. Everybody here, I'm sure, is aware of the fact that it is a super hot topic right now about whether you should use group attributes like sex, age, and race in a clinical risk score. And the Fun fact is that they're already used, right? We already, for decades in logistic regression models and decision trees, have been using demographic attributes like sex, age, and race in clinical risk scores. That ship has sailed, that exists, okay? The problem is, even though your intuition might be, oh, there's more data, use it, it'll make the model better. Well, of course, it'll make the model better overall, but if you use group attributes, it can result in worse subgroup performance, even though, of course, it has to improve overall model performance. So here, I train a simple logistic regression model to predict sleep apnea. When I include sex and age, it's worse for younger male and older female patients. But it is hidden by the fact that it's 1% better on average. And so if you were a younger male patient, you'd say, give me the old one. I don't want to tell you what my sex and age are because you're going to use that. And then the model will be worse for me and patients like me. And this happens for two different reasons, right? It's not like a mystery. It happens because we have either model misspecification, where a model cannot capture necessary interaction effects between features and group attributes, or because you've used something like empirical risk minimization to optimize for overall performance, and that can result in harm for one group at the benefit of other larger groups. Okay, it's like you told it do best overall and it made a decision. Okay. And this gets worse when we think about higher dimensional models, right? You know, this is just a simple logistic regression model with a countable finite set of parameters. When we're thinking about billion parameter vision language models, it gets even trickier, right? And VLMs aren't just used for fun image generation. Like behind the scenes, they're used for a lot of industrial applications, like zero-shot classification of images and zero-shot retrieval. But in each of these cases, there are great papers by other groups that have shown that there are huge biases in vision language models for generation, classification, and retrieval. And one of the issues right now, and this is an ongoing issue, it's not solved, it's like a real ongoing, we still are suffering from an issue, is that a majority of the vision language model debiasing approaches assume that protected attributes like gender fall into linear subspaces. And this is our inheritance from the BERT transformer model, natural language processing days, where we had that great paper that said like male is to female as computer scientist is to housewife, as king is to queen, right? And that made in our minds this assumption that like, oh, these attributes, if you can just estimate where they are in the latent space and take a diff, right, you get a vector. And so you can orthogonalize and project it out, right? If male is here and female is here, we can just subtract them and then we'll get some sort of balance, right? It turns out, you know, model embedding spaces, especially, you know, in these larger models, are extraordinarily complex nonlinear objects. And so if you're trying to debias a latent space with respect to male and female doctors, you might get worse results for male and female pilots or male and female managers, because this orthogonalization and project out operation fundamentally changes the latent space in ways that are unknowable for other attributes or other classes, right? You're taking this big topology, this big like wiggly sheet, you're picking 2 points and you're just pinching them together. And that causes the other parts of the space that surround the pinch points to deform in unpredictable ways. And so a lot of what we're trying to think about right now is how do we estimate what this topology looks like and how to make the least invasive cut or movement or modification to the latent space such that nothing other than the target that you're trying to affect is modified. And right now, a lot of the debiasing techniques, they really make big changes to latent space, which both affect other classes. So you get this whack-a-mole problem where if you debias for male and female, you get worse, more biased results for black and white, for example. Or they just create huge problems for downstream accuracy, where now you can't retrieve any picture of any doctor because everything's garbage. Another thing we're working on, so you know that's a hard problem. It's ongoing. We have a couple papers, both accepted and under review, at addressing it, but it's open, I would say. Another big open problem is silly things like negation. Right. So, you know, despite their flexibility, vision language models struggle with things we do not struggle with, like negation understanding. If you've ever used a state-of-the-art vision language model, you've probably run into this where if you say, I want something in this image and I don't want this other thing in the image, the thing you said you didn't want will be in the image. So I want a table filled with food, but there's no chairs. There will be chairs. If you say, I want a picture of a dog not on grass, there will be grass. If you say, in a question answering situation, I want you to retrieve an image where the dog is not lying on the floor, the dog will be lying on the floor. Okay. And so it's weird how bad these models are at negation. And we wanted to look into why, specifically because it's funny when it gives you like a cute dog on a floor and you didn't want a floor. It's not funny for the applications that we've been approached for. So for example, if you're using something like Biomed Clip to do medical diagnosis image retrieval, you want people that have chest x-rays with evidence of lung opacity, you want this. If you want people with evidence of lung opacity and no signs of edema, you do not want this. And if you cannot process negation, you will incorrectly give me this. And maybe it makes sense, right? Like thinking about it, like why models are so bad at this. How do we train large vision language models? We do it with contrastive learning, where we say, here's the image and here's the text that describes this image, embed them close to each other, closer to each other than any other sort of unpaired set of image and text, okay? Well, that's great, except that we never describe images as an absence of the things that are not in them. So we don't, for example, say girl in pink dress is jumping in the air, no geese. We don't say a black and white dog jumps over the bar without a hat on its head. We never say there is not a thing in the image when it's not in the image. We only ever describe the presence of things. And so it's no wonder that models can't really figure this out because they don't see examples of it. It's, again, much more important in a medical setting because often in medical settings, especially for medical imaging, the point is negation. The point is to rule out a long laundry list of things. So you'll say there's no focal consolidation, effusion, no pneumothorax, no pneumonia, no. The list of no's is much longer than the yes, even if there isn't is a yes, right? Which sometimes there isn't. And so the first thing that we wanted to do here was try to understand how bad this is, right? And so what we had to do first was build a data set that included negations to do this evaluation. And it turns out if you do simple negations, state-of-the-art models lose performance by over 7%. If you do advanced negation, meaning using commas and not just simple yes, this, no, this, models lose performance by over 20%. And that's just in natural images like these. If you look at medical images, as soon as you include a negation, you lose up to 30% performance in state-of-the-art models like Biomed Clip. And we wanted to understand why this was happening. And the reason it's happening is, so in this plot, every color is an object. So like cat is yellow, or sorry, flower is yellow, cat is pink. And a circle is an affirmation, so there is a cat. And a triangle is a negation, so there's not a cat, okay? And so what you can see here is that clip and neg clip, which are state-of-the-art transform vision language models that are supposed to, match text and images. Neg clip is actually trained, it's supposed to be good on negations, right? All the colors are together. The shape doesn't separate, right? That means that flower and not a flower are on top of each other. Cat and not a cat are right on top of each other. And in fact, if you take contrastively trained clip, which is supposed to be the very best at negation, it does even worse, right? Because it's just isolating all the negations into one part of the latent space. So what we're working on now is trying to address this, just like with the debiasing. But the TLDR is robust learning is very hard. And you only realize how hard it is when you test models on corner cases that they, but not humans, would fail at, right? Like humans don't fail on negation, but models do really reliably. Also, when you train a person to not be biased with respect to gender, they don't suddenly become more biased with respect to other things, right? These are sort of unique model failure points that are hard to anticipate. And so we have to work hard to try to remove them or identify them. The final thing I want to talk about is even if you have the best model, hopefully I've convinced you it will be wrong sometimes. And hopefully I've also convinced you it'll be wrong for subgroups that society might have biases towards. And so we wanted to see we've done several studies now where we've looked at models that are either really bad or compared models that are really good and really bad, and just seen how much they affect clinical action. Because in the end, it almost doesn't matter, whether you add a whatever performance to your model if that doesn't translate to a clinician doing their job better. And I think there's been three big takeaways, and these are not all my work. Some of these are other papers that I love, but they're consistent with work that we've done and that I think are real takeaways for AI in health, which are the losses from bad AI are much larger than the gains from good AI. Of course, you can gain things from good AI, but it better be good. Because if it's bad, the negative impact, the magnitude of that is so much bigger. And this was a great paper that was done in 2020. It's one of the first papers that was using AI with humans for skin cancer recognition. And this is the best figure ever, right? Like they're showing across experience levels, if you give the wrong predictions, it really harms clinical performance. And this magnitude is much larger than the magnitude of improvement if you give the right predictions. So table stakes is build a good model, okay? Number two, and this is a paper that we did, but many, many other papers have shown this in many different ways, many, many subsequent times. Humans are really susceptible to incorrect advice. That's not just true in healthcare, but it is true in healthcare. And it's true even if those humans have expertise. Okay, so even if somebody has had a decade of training in something, when you tell somebody, when you give somebody incorrect advice, it's very hard for a human to dismiss it. And so we should be aware of the level of susceptibility that humans have before giving them information that might make them wrong in some cases. And finally, this weird sort of corner thing, which is the way that you give people advice matters just as much, if not more, to their performance than how good it is. So if you tell somebody to do something, like you must refer them for this, procedure, this operations medication, that shortcuts clinical critical decision-making skills, which is this has been shown in many other domains. It's known for like pilots who have thousands and thousands of hours of training and certification. It's known for astronaut, like it's been shown in many settings where people are highly trained, but they also work with advanced instrumentation. If you tell people to do something, like you just give them a command, you should do this, they tend to listen to it even when it's wrong. But if you give them information, right, like there seems to be turbulence, right, or the gauge gives them information that is incorrect, they're able to look at the disconnect between information given to them and their actual training and critical decision-making skills kick in, and they say, wait, something's not quite right here. But all of that goes away when you tell somebody what to do. And so that matters a lot, and it's rarely studied. And it's certainly not part of any certification or deployment guaranteeing process that I've seen, which is not good. So final TLDR, humans are fallible. Make sure that you test models and humans together in deployment in high risk and uncertainty situations beforehand. And not to, I don't want to end on a down note, right? I do think that this is hard to do. All of these things are very challenging and they're ongoing areas of investigation. But I think that we have some positive examples, in my opinion, of transformative health AI, which means like we're not just taking a bad process in healthcare and making it more like efficient, right? It's still the bad process, it just happens faster. Right. And that's a lot of what I see people doing right now, right? They're like, yeah, we know it's bad, but like it'll be faster now. Okay, that's maybe, different goal. A different goal could be that we want to do more transformative health AI. So for example, I think the Marzyeh and Sybil programs that are doing breast cancer and lung cancer prediction and diagnostics with a sister lab here at MIT are amazing. There's so much work that went into gathering robust representative data sets for that, training a robust algorithm, doing really strong evaluation in consultation with oncologists. And then, of course, AlphaFold was a game changer. Like I knew PhD students who spent like literally their whole PhD when I was a student on like predicting, the folding of this portion of this curl. That was their thesis. And, now we have this magical sort of ability to do protein structure prediction, which is amazing. And so I think if we can focus on not like, let's take this bad thing and like just make it faster, but what would actually like be transformative in a healthcare setting, we can move forward to actionable insights in human health. Thank you.